Math 3 Lesson Summary Video. More Ferris wheels. This lesson is a solidify understanding task, which takes concepts developed previously and helps you formalize those ideas. The purpose of this lesson is to model the sine function graphically and relate the features of the graph to the equation and context. Based on the data you calculated, as well as any additional insights you may have about riding on Ferris wheels, sketch a graph of the height of a rider on this Ferris wheel as a function of time elapsed since the rider passed the position furthest to the right of the Ferris wheel. We can consider this position as the rider's starting position at time t equals 0. So we want to remember some things about our Ferris wheel. If you recall, for our Ferris wheel, we had that its height above the ground, the spoke, the axle in the middle's height above the ground is 30 feet. We know that its radius is 25 feet, and we know that it takes 20 seconds to make one full revolution around the Ferris wheel. So our furthest right position would be here at A. So we'll start by just making a table of all of our different heights so that maybe we can plot those points and get a graph. So if we think about at 0 seconds, we are 30 feet off of the ground. If t equals 0 is going to be A, we're starting right here and we're 30 feet off of the ground. We determined that if it takes 20 seconds to go all of the way around, that means we're going 18 degrees per second. So after 5 seconds, I would have gone 90 degrees. And 90 degrees took me to the very top up here. So we said that 55 feet was the furthest up we could go because that's 30 feet plus the 25. So 55 feet. Another 90 degrees would get me to F. So I'm back to 30. Another 90 degrees would take me down to the bottom. So 30 minus 25 is just 5. And another 90 degrees gets me back to 30. So that was our one full revolution. And then we start all over again. We're back up to 55. Back down to 30, back down to 5, back up to 30. So 40 gives me a second revolution. So now I have some nice points that I can plot on a graph and see what this shape actually turns out to be. And what you're going to see here is it started at 0 seconds at 30 feet. It went up. It came back down to 30, went down to 5, came back up. Notice that it is rounded. So now we have a shape to go along with our graph for the function that we've been working on for the last couple of days. So let's see if we can find some of its key features and capture those in our notes. As we look at the graph, what you'll notice is below is the equation that we had come up for this situation. If you remember, we figured out that the equation that gave us all of these heights with respect to the time, that was our time in this problem, was 30 plus 25 sine of 18x. And now we have the graphical representation to go along with it. So let's see if we can match some things up. If you look at the graph, you'll notice right here, along kind of this imaginary horizontal line is 30 feet. That was that middle of the Ferris wheel. And if you notice, it's really right through the middle of this graph. It goes right through the middle of the graph. This number is our midline. It's where the center of our circle is located. And notice that as the circle revolves, it goes up and goes down and goes up and goes down. We think about the circle spinning in a circle, but time is moving forward. So as time is moving forward, our position on the Ferris wheel goes up and goes down and goes up and goes down. And so it's not just sitting there spinning in a circle on the graph because the time is moving forward. So as time moves forward, we go up and we go down, but this midline is the middle of that Ferris wheel. It's what we're rotating around. So we're always bouncing. We come right back to that midline. We go up, but come back. Go down, but come back. And that's our midline. So we have the midline of the graph. Other things that you'll notice, we have our radius. This was our radius of our circle. We have a name for that in this graph, and that name is the amplitude. You may have heard that word before in science class when you studied waves. If you haven't noticed, this sine function very much looks like a wave. It is a function that is used to model waves, and the height of a wave is called the amplitude. And so this is the amplitude of the wave. It was the radius of our circle. It is how much we are going up and how much we are going down, so it kind of gives us our range, how far we can go from that midline. And so the amplitude does go in both directions from the midline. And it is how far up we go above the midline and how far below we go the midline. And that was that number in our equation. Now, if you remember, the 18 in our equation was our angular speed. So that was how many degrees per second were we going, or how many, if we wanted to measure in radians, we could measure in radians that we were going. It was our angular speed. But it comes from, if you remember, we weren't given that piece of information. We were actually told the one revolution, that it took 20 seconds to make one full revolution around the circle. So yes, this number is always our angular speed, but it really comes from that one full revolution. On the graph, if we're thinking about one full revolution, we started at our midline and we went up, and then we came back down and we kept going down, and then we came back up to where we started. This was one full revolution of our circle, and we call that a period. One period of the function. It's one full rotation of the circle, or one full ride through the wave, all the way up, all the way down, and back to where we started again. And we call that the period. And so the period is an important thing to figure out if you're graphing, because it gives us one full snapshot of the graph. If you haven't noticed, this graph repeats itself. It's this piece of the up wave and the down wave, one full ride on the wave, repeated over and over and over, and it just keeps going. So once you have figured out one period of the graph, you know how to graph the whole thing, because you can get one full piece of the wave, and then you just repeat that over and over again. These type of graphs that do repeat, that are cyclic, in fact, are called periodic functions. That is their name. They are called periodic functions, mostly because they do have that period, one full rotation through that just keeps getting repeated and repeated and repeated over and over and over and over again. So if we know our angular speed is 18 degrees per second, if we're doing degrees like we are in this problem, then to figure out what the period was, we know that one full rotation is 360 degrees. And when I take 360 degrees and I divide it by 18, notice that I get 20. And that's what we knew one period of our Ferris wheel was. So anytime we have that number there, our angular speed, we just have to remember to turn the angular speed into what is one full rotation? How long is it going to take to get that one full rotation to find our period? So when you look at a sine graph, important key features, its y-intercept. Notice that its y-intercept is on the midline. The sine function starts on the midline. So that's where it's going to start. It starts on the midline, it goes up, comes down, and then goes back to the midline. So a key feature, its y-intercept. This particular one didn't have an x-intercept because its midline was so high up that it didn't make it back down to the ground. So x-intercepts will be interesting with these because also notice they repeat over and over and over again. So if you have one x-intercept, you're going to have many x-intercepts because it's going to keep repeating every period. It's going to come and hit the x-axis every time it goes through that rotation. So it's a very repeating thing with the periodic functions. So that's something to keep in mind as well. And so our sine periodic function domain, we talked about this yesterday, is all real numbers. We have no restriction now that we understand what negative angles are, what that means in the context of the situation, and that it can keep going around the circle, so the angles can just keep going. But the range is definitely restricted, and the range is restricted by that amplitude, right? Because that amplitude tells us the highest that we can go and the lowest that we can go, and even though it's periodic and keeps repeating, it's really just bouncing between those max and min points. So a sine function does have maximums and minimums, but it has many maximums and minimums as far as it keeps repeating itself. But it does have a restricted range. It's going to only be between two numbers because we're just bouncing between as we go back and around and around and around the circle. We have a highest point we can reach, and we have a lowest point that we can reach. We began this task by considering the graph of the height of a rider on a Ferris wheel with a radius of 25 feet and a center of 30 feet off the ground, which makes one revolution counterclockwise every 20 seconds. How would your graph change if the radius of the wheel were larger or smaller? So if we think about what the radius is affecting in the graph, we said that the radius went along with the amplitude. That told us how high we were going to go or how low we were going to go. So if we made that radius larger or smaller, we're either going to make the amplitude larger or smaller. And if we think about what that does on the graph, that's the height of the graph, or how big those waves are, how tall are the waves. So when you mess with the radius of the circle, you're messing with how tall the waves are going to be in your graph, or the amplitude. That's what you're changing. If you remember in the equation, that was that number in front of the sine. And if we think about our transformations of graphs, that fits. Multiplying by a number outside of the function stretches it vertically or compresses it vertically, and so that fits. What happens if you mess with the height of the center of the wheel? So the height of the center, we said that the center was associated with the midline. So if we mess with that height, we're changing how far above the x-axis it is or how far below the x-axis it is. We're not really changing the shape of the graph any. We're not changing its wave height or anything like that. So we're not really messing with the shape. We're just moving it up and down. And that fits with our transformations as well. If you remember, the midline was that number that was being added outside of the function. And if we add outside of a function, we know that translates it up and down. And so if we mess with the height of the center, we're messing with the midline and how far from the x-axis it is. And then what do we do if we rotate it faster or slower? So if we're talking about how fast it rotates, we're talking about that angular speed. And we discussed that angular speed is inside the function. Whenever something is inside the function, we know that it's changing the graph left to right. And the angular speed we also associated with the period. And the period was how long it takes to finish one full rotation. So when we mess with the period, if we make it faster, that means we get through this whole wave in a shorter amount of time. If we make it slower, then we're taking a longer amount of time to get through that whole wave. So when we go faster, we're bunching up our wave. We're making it narrower. We're making it a faster period, a shorter period. And so that kind of squishes the graph together horizontally. When we take a longer time to do it, we're stretching out that wave left to right, and it's not quite as bunched up. We get it stretched out a little bit more. So when we rotate the wheel faster or slower, we're changing the angular speed, which affects the period. How does the equation of the rider's height change? So again, we said that the radius, if we were going to give a nice generic equation for the graph, if we have c plus a times the sine of bx, if we think about that as kind of our generic form of the equation, if we're making the radius bigger or smaller, we're changing a, because that's the number that's going to make it go up or down, stretch it higher or lower. If we mess with the height of the center of the wheel, we're messing with c, so we would be changing c, that number that we're adding outside of the function. And if it rotates faster or slower, we're changing b. That's our angular speed. So we're going to change b in the equation.